Welcome to another podcast. In this episode, we're going to be taking a look at applications of trig identities to solving trigonometric integrals. And I actually want to start with the integral that's on the right here, and then we'll show how that impacts the integral that's on the left. The entire goal of this video is to introduce you to what is considered the easy case for evaluating trig functions. Essentially, what we're going to be doing is trying to reduce all of these trigonometric integrals to one of two possible cases. The one case is, as described here, where you have a trig integral involving a single power of a trig function versus one with multiple powers. So this is n greater than or equal to, we'll just say 1 in this case. If you ever get in this situation, then the problem is essentially done because you can solve this using a simple u substitution. The u substitution that we would use in this case would be, let's let u be equal to sine of x. Then the derivative of that is cosine of x dx. And so when we go to make the substitution, we have the integral of, well, if I replace sine with u, it's u to the n times cosine of x dx I replace with du. And so this is a simple power rule. And then if I update it with what u actually is, we're pretty much done. So that's a very simple problem, and the goal is to take any other problem and reduce it to that simple case through the use of some clever applications of trig identities. And so let's start by looking at it in particular for the integral on the left-hand side. So the integral on the left-hand side, as is, we can't do this. If you tried to let u be sine or cosine, then you don't have a single power like you do here. So here our derivative was just cosine. If you try to do that with u equals cosine squared, for example, so if u was cosine squared and we wanted to try the same thing, or if u was just sine, say let's try u equal to sine. So if u is equal to sine, just like it was on the previous problem, then u being sine, my du is cosine, and if I tried to make the substitution there, it would be the integral of u cubed. And then the question is, what do you do with the cosine squared of x? Well, the cosine squared of x is du squared, I guess? I don't know. So the question is, this is not going to work. We can't do that sort of substitution. So what instead are we going to try? Well, like I said, the goal is to reduce this to something that looks like the problem we just did. And the way of accomplishing that is by relying on some of these trig identities. So for example, if I look at sine cubed is the same thing as sine squared times sine. And more importantly than that, I can replace sine squared with something involving cosine. By the Pythagorean identity, sine squared is the same thing as 1 minus cosine squared. So that's what I use to go from here to here. We use the fact that sine squared plus cosine squared is 1. Now, I talked about these trig identities in a previous video, so please check that out if you're unaware of the Pythagorean identity. All right, if I take this and replace it into the integral, then I'm looking at the integral of 1 minus cosine squared times sine times cosine squared. And at first glance, that doesn't really seem to help. But let me do one more small algebraic manipulation here. I'm going to combine the cosine terms. So if I distribute the cosine terms, I'm going to get cosine squared of x minus cosine to the fourth of x times sine of x dx. Now, Is it in the form of the previous problem? I say it is. And the reason I say that is because the previous problem just wanted us to have a single power of a trig function. We've got that with sine here. It also wanted us to have I guess we should say other terms. Wanted us to have other terms that have powers greater than or equal to 1. And we have that. We just happen to have two of them, 1 to the 4th and 1 squared. So a similar substitution to what we made here would work. The substitution was based on the thing that had the power, so in this case it was sine. So over here the appropriate substitution should be letting u equal cosine. So if we let u be cosine x, then what happens is the derivative of u is minus sine x dx. And so you can see if we make those substitutions into the integral above, it changes the integral into u squared minus u to the 4th times, and I replace sine x dx with minus du. So this becomes the integral of, this minus sign is going to flip these, so it's u to the 4th minus u squared, which should be easily integrated. That's the whole goal here. And to finish out the problem, we can substitute back what the original value of u was. I'm getting kind of crowded down here at the bottom, but I think we'll fit it all in. And so the idea is, can we take the trigonometric integral and through a series of applying either Pythagorean identities or half angle identities or double angle identities, can we write it in a form where we expose a single power, and if we can, by exposing that single power, we can do a nice trig substitution like I just showed. So this is considered to be the easy case. So this is the easy case, and the reason it's the easy case is because the power in was odd. So you see over here, the power that we were trying to reduce was an odd power, n equal to 3 in this case. Because of that, this works really well. You can always use the Pythagorean identities to reduce it down when the power is odd. In the next video, we're going to take a look at an example of what to do when the power is even, and that's not quite as simple to evaluate as this particular case. All right, check out that video, and thanks for watching.